So, very warm welcome from Garching, Germany. Good afternoon or good morning for those of you joining us from Europe, from America, or other parts of the world. I am Laila El-Haj. I'm a marketing manager at MSAID, and it's a privilege to have you all with us for our first webinar of the year. Please be advised that this webinar will be recorded for documentation purposes. So today we have an exciting agenda planned for today's webinar, and our CEO, Martin Freno, he will be leading the session. And during our webinar, Martin will share insights from his extensive experience in the industry, focusing on the challenges on computational proteomics. We encourage you to participate by asking questions and sharing also your thoughts in the Q&A session. I think I sent a message previously. I hope you can see the Q&A session. It's on the dashboard at the top. And yes, we will do our best to answer all your questions during the Q&A session that follows. And I will now hand over the virtual stage to Martin, and I will stop sharing my screen so that he can take the center stage and begin his presentation.
All right. Thank you, Laila, for the kind introduction. I hope everyone can see my slides. Can I get a thumbs up if that's yes? Perfect. All right. Thank you very much for joining also from my end. I'm Martin. I'm the CEO of MSAID, and today I will give you a brief insight into what not only I, but we at MSAID think are sort of key challenges in not only computational proteomics, but also proteomics in general. And I'll structure this presentation. I mean, now it's nearly a month after Christmas, but it is structured along the lines of the classical book A Christmas Carol by Charles Dickens. Beautiful story about a grumpy old miser that gets visited just shortly before Christmas by three ghosts: the ghost of Christmas past, the ghost of current Christmas, and the ghost of future Christmas. And in the process, he learns something about himself and how to improve on his behavior and how to be a better person. I myself have not actually read this original. I'm more familiar with Disney's adaptation of it. But in general, it is told in 5 staves. It's a little bit of an introduction, and then we start with the ghost of the past challenges in mass spectrometry in terms of this particular presentation. I'll then move to the current challenges in mass spectrometry and computational proteomics, and then give a bit of an outlook what I think and we think at MSAID will be future challenges for mass spectrometry and computational proteomics in particular. And at the very end, since this is supposed to also be an interaction with you, we have some time for a Q&A session at the end of the webinar. So as I'm going through the slides, feel free to add questions to the Q&A block, preferably the Q&A block, not the chat, but we'll keep an eye on the chat as well, so that we can have a lively discussion at the end of the presentation. Yes, I believe I don't need to introduce MSAID at that point, since you found the link. You know what we do. We develop software for mass spectrometry. But you know, mass spectrometry has not been here since yesterday. We are standing on the shoulder of giants, of course, and mass spectrometry and proteomics in particular has been developed for multiple decades by now. And here I've taken just a little bit of a timeline from one of the very great ASMS history posters. If you've ever go to ASMS and get a chance to look at them, it's very educational. I like to walk past them every single time I visit ASMS. And they highlight sort of key advancements in the past decades that brought us to where proteomics is today. And I can never even fathom to talk about every single one of them. I just want to pick 3 key advances that I think sort of visualize where we were at as a field and where we are as a field right now. And these are very focused on the analyzers. and I'm picking now out. I'm picking 3 analyzers here, totally arbitrary selection, but I think they visualize quite nicely what I'm trying to tell. We started out with analyzers such as the linear ion trap, which were very fast, very sensitive, but unfortunately did not have that much resolution that we would want to have when it comes to both proper identification and quantification of peptides. All of that was tackled with later analyzers, such as, for example, the Orbitrap, which tackled the resolution sort of deficit that the linear ion trap had. And that brought us resolutions of 240, 480, and even higher resolutions, K that is, of course. But unfortunately, these analyzers are not as sensitive as linear ion traps, and they're also not as fast. So it sort of, in my opinion, was a natural move of the entire field, especially on the vendor side, to move towards TOFs as they combine the best of all worlds in that sense, as they are very fast. They're very sensitive with the use of electron multipliers and photon multipliers nowadays, and they have just enough resolving power to let us work with our favorite peptide ions and identify peptides from very complex mixtures. But even some of these are even have a resolution high enough to resolve TMT channels also of the new TMT Pro reagents. So it was somewhat of a natural move, and I like to think about it as we increased in sensitivity, we increased in scan rate, we increased in resolving power, hence we increased in total data density. And if you've run a couple of experiments lately on, say, an Orbitrap and now on one of the more recent TOF instruments, you will see that if you acquire the same gradient length, you will see that your data is just exploding in size. And I believe this will be, without wanting to spoil the end of the presentation, this will be one of the challenges of the future, that data density is growing very rapidly, and especially organizations such as the EBI that hosts Pride, or repositories such as Massive will have to take a very close look at the infrastructure to see how they can handle the data that rolls off modern instruments running 24/7. But that is here now a focus on the instrument side. What has happened on the software side? And if you're talking about computational proteomics in particular, you of course have to ask the question: well, how do we analyze the data that rolls off the mass spectrometer? And this, I think, here is a very nice review on the topic. It's relatively dated in terms of the search engines that it considers and the landscape that it covers. So it would be great to have such a review, a more recent one that also includes other search engines that are only here on the right-hand side as sort of honorable mentions. But if you talk about search engines, you of course have to start with Sequest as sort of the first search engine that was utilized widely. And you cannot forget Mascot, of course, since it's still very widely used, especially in industry. But in this graph where you have basically the number of citations along years, you see that more recently search engines such as Andromeda and MaxQuant are spiking in popularity as measured by the number of citations. But I believe this will have changed by now already, and search engines such as Fragger will be much more dominant in a graph like this. But all of this is only looking at DDA search engines so far. Hence, I've listed here a couple of DIA search engines, since most of the field is now taking a very close look at DIA and whether that could be a viable workflow for the questions one might want to answer. And of course, Chimeras is also part of all of this, but in general, there's just a whole variety of different search engines. So is there sort of can we detect a common theme, a common trend that search engines tend to move towards nowadays. And I would say yes, there is, and I think that the trend goes towards using spectral libraries for identifying peptides from tandem MS spectra, either acquired or predicted. And why we do this and why several software developers do this is pretty clear. So here we have a prototypical MS2 spectrum with MZ on the x and intensity on the y-axis. Normally, if we go to the shoulders of the giants and analyze a spectrum like this with Sequest, this is what it would look like. Sequest would generate all theoretical fragment ions, would match them and ask the question, how many fragment ions have I matched? How many fragment ions have I not matched? Calculate a probability of matching this number of ions randomly, and be done, and then rank peptides by such a score and try to determine FDR. But as we all know, the information encoded in these intensity fingerprints of a tandem MS2 spectrum can very well be used to actually increase our sensitivity of calling correct peptide identifications, which is the reason spectral library search engines exist. So we all know interpreting spectra, interpreting not only the MZ dimension, but also the intensity dimension of spectra is something that is very desirable and can increase sensitivity in terms of peptide ID, because one can calculate other scores, intensity-based scores, such as, for example, spectrum similarity. And that allows one to distinguish between very similar peptides in very frequent cases. But that's where work has been put into mostly in the past decade, let's say, especially with predicted libraries. So what are the current challenges in mass spectrometry and especially in computational proteomics? What is there still to be solved? And one thing that I would like to confess immediately is that I haven't been quite honest with you from the get-go. This is actually not really what a mass spectrum looks like. And I believe every one of you knows that. A mass spectrum looks more like this. So it's a whole lot more complex. You don't only have the canonical Y and B ion series and various different charge states, but you have various neutral losses. You have isotopes in there. And all of that, all of those are actually fragment ions that you can use in order to interpret the experimental MS2 spectrum in order to get an idea about what peptide generated it in the first place. I will use this sort of representation here throughout the rest of the presentation frequently. It's a sort of the classical mirror plot here. On the below the x-axis, you have the experimental spectrum. Above the x-axis, you have a reference spectrum as it was acquired by the Technical University of Munich. I'm very gratuitous to that they shared the data with us here in this case. Given that this is here an HLA peptide is non-tryptic, you see that there's so much more information to go by that we would ignore if we would just focus on B and Y ions of charge 1. And that already brings me to a challenge that I think is currently being tackled, especially in the context of DIA search engines, and that is that spectral libraries very frequently are filtered. And in my opinion, the filtering of spectral libraries can be very dangerous to do. Why would that be dangerous, you might ask? I've brought you here an example where I believe the filtering of the spectral library that in this case Diane used for its identification led it to believe that it has a confident identification, but in fact a wrong identification. So here, just looking in a vacuum at this particular mirror plot here, you have now the predicted spectrum and only the matched fragment ions of the predicted spectrum below the x-axis, and the experimental spectrum, again, only the matched fragment ions above the x-axis. And you can see the fragmentation pattern of these ions matches very, very nicely. It has a spectrum similarity according to Diane of 0.77. So normally you would be calling this a great match and move on to your next identification. However, if you look at the same identification in chimeras, which failed to identify the very same peptide here, you see that chimeras itself actually considered many more fragment ions to be matched to the experimental spectrum, some of them which are matched, but we lack the Y7 and the B5. These two fragment ions are predicted to be there by chimeras. They are not found in the experiment, and that is actually punished, reducing the spectrum similarity to 0.36, and chimeras in turn rejects that particular identification here. But it's not rejected based on the spectral angle. It's a bad spectrum similarity in the first place, but because the base peak of the prediction, the most abundant peak of the prediction, is not actually found in the experiment. Diane filtered its spectral library to not contain this Y7. In other settings, that Y7 will be there. It will also be the base peak. So I would argue filtering this Y7 out and then calling an identification without it is dangerous business, because it opens you to identify seemingly the correct sequence while it might actually be a sequence permutation, just a partial sequence match. Hence, I would argue, let's filter spectral libraries as little as possible in order to extract as much information as possible out of the data. But filtering spectral libraries has also a second disadvantage, and that is if you do filter your spectral libraries, you open yourself up to artificially increase your spectrum similarities just by virtue of having filtered your library. Here we look at a subsection of IDs that was identified by Diane and was not identified by chimeras. And we just asked the question on the in the plot on the left-hand side, what is the number of predicted fragment ions for these identifications in the library that Diane uses, or that in the spectra that chimeras predicts for these particular peptides. And what you can see is chimeras predicts a whole lot more fragment ions. And Diane only, in median, I believe, predicts 6 fragment ions. And everyone that has worked with correlation metrics knows that as you reduce the number of data points based on which you calculate a correlation, the easier it will be to actually achieve very high correlations. So seemingly, Diane on these identifications has a higher spectrum similarity, but this is only by the virtue of having filtered its spectral library down. So these are spectrum similarities that look higher, while in fact they shouldn't be. I threw that at you right now without actually going into a distinction between how we do identifications in DDA versus in DIA. So maybe it warrants bringing everyone on the same page. I believe many of you are interested in computational proteomics in the first place, so it might not be news how identification and quantification is done in DIA versus in DDA, but let's briefly go over this. So here we have on the left-hand side a simplified library-free DIA data analysis, where we start with a spectrum-centric identification of peptides from either directly the DIA data or a DDA measurement of the same sample in order to generate a library. And that library is then used to basically extract XICs of fragment ions from the DIA data, perform a second level of quote unquote identification, and then quantification based on fragment ion intensity area under the curves of these XICs. And in DDA, we have identification in MS2, and then quantification in MS1, where one maps the precursor mass of the identified peptide to the isotope envelope in the corresponding MS1 scan, and then traces those along retention time in order to arrive at a quan value. But the key point here is, if you want to do proper quantification, you have to have a certain number of data points across the peak. So another challenge that I think we are struggling currently with is that current methods very often are not really optimized towards accurate quantification, but will try to boost the number of identifications at the expense for quantitative accuracy and precision. And how is that? Well, just consider this particular example here on the left-hand side. You have 10 data points across the peak, 10 hypothetical data points. If you were to reduce this to only one data point across the peak, you would end up with triangle XICs, where I would question whether you can actually use those for proper quantification. Now you would say, oh, I would never measure my data like this. Why would I measure my data like this and only generate one data point across the peak? That wouldn't be a great idea. Well, let's consider the following thought experiment. Let's assume you want to set up an experiment with 1,000 Thomson, covering 1,000 Thomson of MZ range in MS1, and you're working with a 2.5 second cycle time at 20 Hertz. That just directly equates that if you want to have 10 data points across the peak, you need to work with 20 Thomson windows. 20 Hertz is a typical speed of a Orbitrap. 2.5 second cycle time is a typical cycle time of an Orbitrap. And 20 Thomson windows are typical Orbitrap isolation windows. If you go now and you want to do that, the same measurement, still with 10 data points across the peak, but now in 0.25 second cycle time, you have to go to 200 Hertz and still maintain 20 Thomson windows. 200 Hertz is the specification of, for example, the Orbitrap Astral. So in 0.25 second cycle time, you can basically cover the entire 1,000 Thomson mass range with 20 Thomson windows. But what is currently suggested is to measure with 2 Thomson windows. And I fully second that. It's a great idea to measure with 2 Thomson. It increases specificity on the identifications that you can obtain in DIA data. But if you wanted to cover this 1,000 Thomson mass range with 2 Thomson windows in 0.25 second cycle time, you would have to have an instrument doing 2 kilohertz. There's no instrument that can do that as of right now. So I would advise, or it's just my opinion, you can do whatever you want, but I would, I'm of the opinion that if you have a fast TOF instrument, you have to make the choice to either decrease your gradient time if you want to go high throughput, or decrease your isolation window width, but don't do both at the same time, because you will otherwise end up in the one data point across the peak area where quantification is going to be difficult. And of course, we want to have both accurate and precise quantification, right? Right? Exactly. That brings me to one very nice paper, in my opinion, that I encourage every one of you to take a look at. And that's basically a study that investigated whether our current measures of evaluating whether our experiment is precise and accurate are actually overused in some sense, and they particularly target the coefficient of variation, and they target it in a sense as they say, well, it's not really great to only look at the coefficient of variation as a metric for quantitation quality in proteomics. So what did they do? Just one brief excerpt from the paper. They studied how the coefficient of variation changes when one introduces intentional errors in the quantification. What they did is they quantified in MS1 and they matched, as I mentioned earlier, their MS2 identifications to MS1 signals, either with 5 ppm and a very tight retention time window, or they integrated all signals in a wide retention time window of 10 minutes and matched precursors that are 50 all the way to 2,500 ppm apart from the true signal in MS1. And as you see here in the plot B, what you can see is that the CV, as you increase the matching tolerance from 50 ppm all the way to 2,500 ppm, the CVs of this 3-organism mixture experiment, where they have E. coli, yeast, and human together, they decrease. So basically, you have lower and lower CVs the more wrong data you basically integrate. So just based on this plot, you would draw the conclusion, oh, great, I can now match my MS2 precursors to MS1 signals with 2,500 ppm and obtain great CVs for my quantification. And but the diminishing returns will be immediately obvious to everyone if one looks at the expected log2 fold change. So here auto is this 5 ppm, 0.35 minutes matching tolerance. There you see that you cover the expected ratios of a log2 fold change of 2 for E. coli, 0 for human, and -1 for yeast pretty well. But as you increase your matching tolerance to 2,500 ppm, the matching tolerance giving us the best coefficients of variations, basically the accurate recovery of our log2 ratios is gone. So they go on then in the discussion to state that if you work with a tool that has worse MS1 signal extraction or loose force discovery rate, it will provide lower but senseless CVs. So pay attention when you evaluate different search algorithms and make judgments based on only coefficient of variation. In these particular experiments, looking at, for example, the correctly called number of differential proteins would be a much better metric for evaluating quantitative performance in an experiment like this. So we say loose force discovery rate here. So if we control force discovery rate, then we are good, right? Well, sort of, but the question arises, at what level shall we control our force discovery rate? And we would argue that FDR must be controlled at the exact level where you actually report your identifications. So here, just a brief example, we have data from chimeras. We count the number of unique modified peptides in the data set, and we filter at different FDR levels. So we filter either at the correct level, the level of modified peptides, or we filter at the level of PCMs, which is precursors, so adding charge to modified peptides, or PSMs, so adding the scan information to precursors as well. And as you can see, if you filter at lower roll-up levels, so you filter at the PSM level, but you count the number of unique modified peptides, then you essentially overestimate the number of identifications by 26.5%. This is a wrong number of identifications. You have to control FDR at the modified peptide level if you want to count modified peptides. The same holds true if you count the number of PCMs. Then again, you have to filter your data at PCM FDR or precursor FDR. But how do we actually judge whether different tools that are available to be used for the analysis of, say, DIA data actually control their force discovery rate appropriately? Well, luckily, there's an experimental design that allows us to do this, and it's called an entrapment experiment or double decoy experiment. Just briefly, I don't have a detailed explanation on what an entrapment experiment is here with me, but essentially what we're doing is we try to evaluate whether the target decoy-based FDR that a given search tool calculates corresponds to the true FDR in a particular data set. Measuring the true FDR without having a ground truth data set is very difficult. So what one does instead is one adds additional peptides to the target database that one knows aren't there. And if those sound very much like decoys, well, that's because they are. We add essentially decoys to our target database, and then these decoys that we add to our target database, we know shouldn't be in the sample. There are people who use different organisms, for example. We would argue that it's much better to use shuffled sequences of the same organism, and then every identification in this shuffled database on this or this other organism database is by definition a wrong identification. And then you can count the number of wrong identifications at a given FDR cutoff in order to establish whether the FDR calculated by a given tool corresponds to the true FDR. We would argue that for this particular experiment, one has to use very big entrapment databases in order to capture all the false identifications into the entrapment space rather than the decoy space. If one does this for chimeras, what one sees is that if one plots the FDR versus the entrapment FDR, then basically chimeras lies on a line that is very close to the diagonal, meaning that we neither overestimate nor underestimate the FDR. And if one does this, instead of cutting the data set at FDR, one can also cut the data set at entrapment FDR horizontally here, and then count how many IDs survive, essentially, the filtering. And what we see here on the right-hand side, comparing chimeras to Diane and Spectronaut on that same data set, filtering either on FDR or on entrapment FDR, what one sees is that for chimeras and Spectronaut, it doesn't really matter whether one filters at FDR or entrapment FDR, but for Diane, it certainly does. If we filter the data set for Diane at entrapment FDR, Diane loses about 24% of its identifications. So we would argue it is very important to verify whether the FDR calculated by a given tool is the actual FDR in the data set, and entrapment experiments are very nice to do that. But still the question remains, what about these other IDs that are exclusive to a given search engine? Well, we looked at this particular data set at some of these identifications for which chimeras, for example, has an FDR bigger than 1%, and that are, for example, or that are exclusive to Diane fully, or that are common between Diane and chimeras. And what you see is these identifications are at the lower end of the detection limit, which on its own is not bad. Diane could just be more sensitive in that area. However, if one now asks the question, well, these IDs that chimeras doesn't have, but Diane and Spectronaut detect, how well do they actually agree on the quantification? So here we have the ratio of the quan value of Diane divided by Spectronaut for the IDs that are common between chimeras, Diane, and Spectronaut, and then for the IDs that chimeras did not identify because they didn't make the FDR cutoff. And you can immediately see that for these IDs, Diane and Spectronaut actually disagree more about the quan value than for the common IDs. So we would argue that these are shaky identifications that at the very least should be looked at individually if one wants to base an entire postdoc on following up on a particular peptide ID in an experiment. That brings me to one sort of key point that I would want to make, since we are already pretty deep in DIA data analysis, and that is that data completeness in DIA is heavily influenced by the way DIA data is searched nowadays. I showed you this simplified library-free and DDA workflow, and what you can see is that here we have identification twice in DIA, and in DDA we only identify once based on the MS2 spectra. In fact, this is how the database sizes look at for these different searches, just to visualize the amount of targets and decoys that go into these searches. For DIA, you start out with the full target and decoy database, and then at the library generation step, that target and decoy database gets shrunken down substantially, because usually a spectral library is filtered to 1% FDR after the first identification step, and then an equivalent number of decoys is added back, substantially reducing the search space. This is not done for DDA at all, right? By the way, given the fact that this library is generated for multiple runs, this reduction of search space across multiple runs is what DIA people, at least Diane, call match between runs. That is a completely different term on DDA. Typically on DDA, we refer to match between runs where we identify a precursor in one raw file and match it to isotope envelopes in multiple other raw files where we haven't actually identified that particular precursor. But that's just on the side. The practice of reducing the search space in DIA is something that is not really done in DDA. Nobody does this. Nobody does a first run of identification and then filters down the search space to do a second run of identification. I'm not saying that this is wrong. I'm just saying that it's not done on the DDA side whatsoever. And as a field, we should agree on common standards for all the different methods, because at the moment it feels a bit as though the field of computational proteomics is divided between DDA and DIA. But technically, if we have instruments that go 200 hertz and faster, I believe we shouldn't have that division anymore, because in the end, nowadays, if you run 60-minute gradients with enough data points across the peak, you can actually run a DIA experiment with 2 Thomson windows, effectively making it a DDA experiment window-wise. And in my opinion, at that point, DDA should even sample the gradient that you see much better than DIA, because in DIA you will always sample areas where you will never have any precursors eluting. All right, that was a lengthy stretch of current challenges in mass spectrometry, and I would like to switch gears now, talk a bit about the future challenges of mass spectrometry. And one of the future challenges that is associated with a topic that is very dear to my heart, and that is false discovery rate, is the error propagation in large data sets. So we are not the first ones to think about this, of course, but consider the following thought experiment. If you have multiple experiments that you search together, and you add raw files to a set of experiments, and you keep searching more and more data, what you will end up with a classical target decoy approach is a plot as the one here on the left-hand side, taken from a paper by Zawitsky et al., which basically shows that the number of targets rises sharply and then saturates as you add more experiments to the list. But the number of decoys sort of starts to increase and increases further, because these IDs are random. And hence, IDs at 1% protein FDR will initially start to increase and then start to drop. The authors of this paper proposed a method that gets around this. It's called picked FDR, that is implemented in Proteomics DB and solves part of the problem. And from the same group, more recently came another paper following up on this idea, basically stating that the competition of a target protein versus its decoy protein could be extended also to the protein group level. So we think the picked protein group FDR is a valuable way of trying to reduce this diminishing returns as we add more and more experiments into, say, databases, and still need to control FDR appropriately. So we like this approach very much. And just to briefly outline what this actually means, the picked FDR approach essentially pits a target gene and all its peptides against its corresponding decoy gene and all its peptides that map to it, and then selects so only leaves one, that picks one of the two, hence picked FDR, and that is the one with the better score, essentially. On the protein group level, the authors had to solve the problem of razor peptides, but I encourage you to read that paper. I think it's pretty good, and I would argue that we might even need something like picked peptide FDR, as we increase our sequencing depth with mass spectrometers that are faster and faster. Yes. Speaking of mass spectrometers that are faster and faster, and the poor people over at the EBI and over at Massive, with these new generation of mass spectrometers, we'll be able to generate terabytes of data very, very quickly. So some of the future challenges of mass spectrometry will revolve around actually optimizing our infrastructure to handle that data and the storage of that and the transfer of that data efficiently. And I would argue that sort of recent trends we should be very well aware of, and that is we seem to live in a bar chartopia. People nowadays disregard the importance of accurate quantification in favor for ever longer list of identifications. And I think we need to refocus on what is very important, and that is, of course, the quantification. We were very surprised when we saw in recent talks that quantitative results at 5 to 20% FDR were reported and not frowned upon. I personally think that's not a good idea. So please stick to conservative FDR estimates. Otherwise, our field is in big peril. And of course, all of that puts a lot of pressure on software tools to accurately control FDR. So as a tool developer, and we consider ourselves a tool developer, we feel the responsibility to accurately control FDR and to report genuine results to our users. And that's our responsibility. But we also think that the user itself has an increased responsibility to actually look at the data and make judgments about critical identifications that lead to biomarkers, because you don't want to be in the seat where you've spent a postdoc on validating a particular biomarker, and it turns out that this is just a wrong identification that you've accepted, either because of too high FDR or because you failed to look at the raw data and convince yourself that the peptide is actually there. But this is not only about computational proteomics and the instruments that are getting faster and faster. This is also about the biochemists that actually prepare the data. So if you think about sort of the cycle of that, which starts at the sample preparation step, goes over to LC-MS, and then data analysis, given the instruments that we have at our disposal nowadays that are very fast, very sensitive, and can pick up on minute signals in samples, we have to make sure that our sample preparations are as clean as ever. I believe we need to be an order of magnitude more clean in our sample preparation in order to actually not stress the data analysis tools at the very end. Because if your sample is not clean and you have plenty of background ions to match identification to, then there will be software tools which will happily take these background ions and assign them as peptides. And of course, it has to be tackled from two angles. I believe the software developers need to be very well aware of that, and we are. But also the biochemists among us should strive for sample preparations that are as clean as possible. So yeah, with that, I'm at the takeaways. So essentially, proteomics is rapidly moving towards high throughput studies, population scale plasma proteomics, single cell. We require for these studies, of course, very advanced hardware, so very fast and sensitive mass spectrometers. But if we want to combine narrow isolation windows with short gradients, these mass spectrometers need to become even faster. So here's the shout out to the instrument vendors. Let's hope for a 2 kilohertz machine next year at ASMS. But of course, software also needs to adjust to the challenges that come with these new single ion counting devices. We need to be able to score not only the presence but also the absence of ions. So that goes in the direction of filtering your spectral library. Very important in my opinion. And tool developers have to be aware of the need to accurately estimate force discovery rate, because everyone essentially relies on accurate reported force discovery rates, because only then are we able to properly compare tools and workflows. We try to educate the community as much as we can when it comes to how to properly compare tools. So if you have any questions, feel free to reach out, but we'll continue to do so also this year at ASMS. And just to sum all of this up, I think we've been now for quite some time in the healer phase of testing different measurement or acquisition methods and different analysis schemes. And we've somewhat ignored the quality of our data, at least to some degree. So I would argue we need to generate less, more beautiful, and not more, less beautiful data that goes out to the fields of single cell proteomics and population scale plasma proteomics. But I'm certain that many of these challenges are solvable. They're solvable if the community stands together and works on these challenges together. And I believe some of the people that are here will certainly make big contributions to that. And with that, I'm at the end of the presentation. Of course, I'm here just telling a story, but I'm fortunate enough to work with a great team of people that develop the tools that we develop here at MSAID, namely Chimeras, Inferis rescoring. And it's a great atmosphere. We are hiring, so if you are looking for a job, feel free to reach out to us. You can, of course, request a free demo of Chimeras by following this QR code here, but it's also on our website. And with that, we essentially arrived at day 5, the discussion on how to tackle these challenges. And I'm happy to take your questions and kickstart some discussions in the remaining minutes that we still have in this hour. Thank you very much.
Thank you very much, Martin, for your presentation and your valuable insight on computational proteomics. I don't see any questions in the chat so far. I don't know if we give a few seconds so that they can write the questions if there is any. Oh, there comes one. What is the decoy when we have a spectral library? To me, it is simple. That is a decoy when we have a set of sequences. Just reverse all sequences. When we have a library, maybe you can explain a little bit more about. Yeah. Thank
So
you,
I think it's a great question. So I was talking about the trend in computational proteomics to move towards the usage of spectral libraries because it increases sensitivity. And you rightfully asked the question, well, how do I generate a decoy spectral library? You can't acquire a decoy spectral library. At least that's the thought process of that you would have if you come from the classical library generation regime, where you acquire some DDA data, you analyze that DDA data, you extract either consensus spectra or representative spectra from your DDA data, make a spectral library. That spectral library will not contain decoys. But I believe now with the advent of deep learning, we can actually predict those decoys with the same accuracy as we predict the fragmentation pattern of the target. So I would argue that if you want to generate both targets and decoys fairly, and you want to generate a spectral library for those, then I would argue that you have to generate it with deep learning based predictions from the same model, and that will essentially end up so conceptually just like sequest calculates all theoretical B and Y ions for targets and decoys, you calculate all theoretical B and Y ions and their intensities for targets and decoys. So I think proper decoys in spectral library search engines should be predicted.
Thank you, Martin. We have a second question. Do you have any idea why the Y7 in the spectra on slide 13 is filtered out by Diane, although it is the base peak ion?
So it's a great question. The reason I don't know the reason, to be honest. And I am incredibly confused because sometimes it is filtered out and sometimes it isn't. When we change to a different database, which is simply a big entrapment database that contains the very same target sequences plus additional sequences, then what we see is that Y7 ion is actually there, Only when you don't search against the big database, the Y7 is gone. So we are actively looking into why certain fragment ions are filtered out, whether that is data-driven or not. We don't know as of yet, but that's an active area of investigation. If anyone else has some idea there, that would be, I would love to know. Yeah.
Thank you, Martin.
I've seen
Oh,
another
yeah.
question in the
Go
chat,
ahead.
I think. Follow up on the decoy. How about decoys when you have PTMs? So essentially, it's a natural extension to what I said earlier. If you're We know that certain PTMs will have a substantial influence on the fragmentation pattern of a given peptide. And let's pick an example. When you have phosphor, for example, and you add phosphor to your sequence, you will also observe the loss, the neutral loss of the phosphor group. You will also see other neutral losses, and the intensities of the other fragment ions will be influenced. So I would again argue decoys and true targets at the PTM level can be generated also with models that are aware of the fact that PTMs will change the fragmentation pattern. For Inferis, as we develop it, this is the case. So we've trained our most recent Inferis model also on phosphorylation data. And Inferis predicts based on 3 parameters, and that is essentially the sequence, including its modifications, the charge state, and the collision energy at which we want to predict the spectrum. And given the fact that we have the PTM information already encoded in there, predicting both target and decoy spectra for different PTMs is essentially just feeding them into Inferis and obtaining the prediction for them. And when we look at these predictions, we see that PTM, so phosphorylation, if we switch the position of the phosphorylation, we work with isomers of a phosphorylation, and then we see that the intensities of other ions that don't carry the phosphor will change. So there is information encoded also in ions that don't carry the phosphorylation modification. So it's again deep learning to the rescue, if you will.
Thank you, Martin. I don't know if you have access to the Q&A, but we have a new one. In your opinion, how much deeper is there realistically to go with regards to the IDs to current samples? Are we at the limit already? Yeah.
So personally, I believe like looking at the DIA data that we look at now day in and day out, I believe that we've hit a point of saturation by now. So I don't think that we will see a substantial increase in the number of identifications. So we won't see a doubling in IDs from the same data in the foreseeable future. I think the reason for why do I think that way? If we inspect the overlap that the different search engine produces, we tend to always see that they agree on the majority of their IDs, and there's just a minute non-overlap that effectively you have to ask yourself the question, are these all true identifications? If they disagree on the quan, are these genuine identifications? We are actively investigating into that non-overlap between different search engines and ask the question, are these actually IDs that we could rescue? So just looking at the slides that I showed today, just naively, one would say, oh, maybe we can increase the number of identifications still by 40%. Personally, I would not believe that. I think that the increase in IDs that is possible is far lower than 40% of what we can currently achieve.
Thank you very much, Martin. So I don't see any more questions.
I see one. Are you considering predicted IRTs for decoys? So just the same way as we predict fragmentation pattern for peptides that either do or don't carry a PTM in Inferis, we also predict the IRTs for decoys. So there's no difference. And the reason why I think this is valid to do is pretty simple. We define what a decoy is, right? So in double decoy experiments, people typically take Arabidopsis as their entrapment database, for example, and they say, well, I don't expect any plant peptides to be present in my human sample. But the plant peptides are just genuine peptides, right? A decoy is always context dependent. When I search a human sample, a plant peptide might be a genuine decoy. When I search a plant sample, a human peptide might be a genuine decoy. But a peptide is a peptide is a peptide. It's just a sequence of amino acids. So I would argue that predicting both fragmentation spectra and IRTs will allow us to judge whether a given decoy or a given target should win over an identification given a particular spectrum. So yes, we do predict IRTs also for, well, not IRTs, we predict retention times, but we predict retention times also for decoys. Yes.
Oh, there are two more coming. If Inferi has a high confidence peptide but doesn't match site-determined ions for localization, does it penalize the whole peptide? Are peptides probabilities valid for the base peptides?
So at the moment, PTMs such as phosphorylation, when we calculate, Chimeris doesn't calculate localization probabilities for them yet. As Chimeris is implemented currently in PD, we use PTMRS for the localization of the phosphorylation site. So we feed the results of Chimeris to PTMRS, but PTMRS itself is not aware of intensities, right? So PTMRS still goes via the traditional scoring scheme of evaluating all theoretical B and Y ions and calculating a probability based on that. So if you're working with Proteome Discoverer, then PTMRS and the localization probabilities it calculates are not based on fragment ion intensities, and hence will also consider presence and absence of site-determining ions, I believe, but I don't recall the PTMRS paper from the top of my head now. Okay, the next one, immunopeptidomics, I see. Do you think in Ferris 5% FDR is a good FDR cutoff for peptide identifications or more stringent? So what we typically see when we do in Ferris rescoring on HLA data, what we typically see is a factor 2 in the number of peptide identifications that we can obtain at 1% FDR. It really depends on what your question is, right? So if the question is you want to find a tumor neoantigen and you want to follow that up in clinical studies, I would think 5% might not cut it anymore. I would even consider going to 0.1% instead and being more stringent and filtering down your data even more, because whatever survives that cutoff, you can be more sure that that the identifications that you obtain are correct than with 5%. It's maybe not the correct phrasing. You can't be more sure, but the proportion of wrong identifications among your identifications will be that much lower if you work with 0.1% as opposed to 5%. However, if you're doing a screening only to generate some leads that you then follow up with other experiments then further down the line, maybe 5% is fine. It really depends on the question that you're asking and how much specificity you want to have at a given stage of your workflow.
Thank you, Martin. And we have one last one regarding also FDR control. What is your take on FDR controlling using peptide-centric versus spectrum-centric approach?
Yeah, so I briefly outlined this two-step search that is done in peptide-centric algorithms such as Diane, but also Spectronaut, where first the library is generated, then filtered at 1% FDR, and then this filtered down library is used to do another round of identification. Of course, then you need to add back decoys in the same proportion. But the effect of this, at least what we see, is that typically data completeness due to this reduction of search space will be substantially higher than if you were to not do that. It's a bit of a difficult question in the sense as yes, the data completeness is higher, and that is very desirable, especially if your data is very homogeneous. So if you're working with replicates or if you're working with treatments of the same organism. But if you're looking at population scale plasma proteomics studies, an approach like this might actually generate data completeness where you don't really want it, because it opens you up, or it exposes you to potentially matching some spurious signal to a peptide that was confidently identified in a different raw file. Many of these identifications might be genuine and might be correct if your experiment is very homogeneous. But the moment you move to more dissimilar samples that you all throw together in one search, that will be wrong even more and more often. So it's a balance. I think it can net you additional IDs and additional data completeness for very homogeneous experiments, but it can be dangerous for non-homogeneous experiments. So I think of peptide-centric FDR. So the FDR in the second step, more like a quantification FDR, if you will. The actual identification was done at the PSM level, in my opinion. So all other levels, in my opinion, are more quantification FDR, if you will. It's not a term that sees much use, I believe, in the literature, but we think about this a lot and how to work with this internally.
Thanks, Martin. We have a last one. How do you do FDR control at the modified peptide level without knowing whether two separate isomers can confidently be called two separate isomers?
So Chimeras, what Chimeras does is for a given spectrum, we only report currently one isomer, right? So if we have multiple isomers that could potentially explain a given experimental spectrum, we only pick the one that best explains the signal that we observe. And hence FDR is controlled at that level. When we do localization, and we are working on an own localization module at that point, then we would attach probabilities to those, but identification FDR would be controlled at the precursor mass spectrum combination, if you will. I hope that answers your question, Danny. If not, just shoot me an email. Thanks.
I guess the last one, how does Inferis works with TMT peptides?
So Inferis can predict TMT spectra, no problem. We've trained it on TMT data. And if you use it, then if you use Inferis as part of Chimeras, then the immediate reaction is, oh, why would I deconvolute my chimeric spectra? Why would I want multiple identifications per scan? I can't use these TMT quan values then afterwards, because then the spectrum is convoluted. And I would say, yes, exactly. That's the point, because what you actually want is you want to know whether a given MS2 spectrum is convoluted, so has multiple precursors in it and the signal of multiple peptides in it, because then you know that your ratios in that scan will be compressed to some degree. So what we advise people to do when they search TMT data with Chimeras, to always essentially filter their PSM list later on an additional filter column in Protein Discoverer that is called normalized Chimeras coefficient, I believe. And that ranges between 0 and 1. And the interpretation of that is, if it's 1, that means all of the intensity that we could explain for this particular experimental spectrum can be attributed to a single PSM, and this is this PSM. If that value is 0.5, that means 50% of the explained intensity can be attributed to this particular PSM, meaning that an additional 50% was explained by a different peptide. These particular scans would then you would remove, in my opinion. So typically, I think the default, we recommend 0.8. So we recommend to use 80%, a 0.8 cutoff, meaning that 80% of the intensity in a particular scan can be attributed to one peptide, and then use these scans only for TMT quantification. That will, of course, reduce the number of PSMs that you can work with. Luckily, Chimeras gives you a couple more to work with in the first place. But if you do that filtering, then essentially on MS2 level, you can filter out the scans that suffer from substantial ratio compression. And now you might ask, why would I want to do that with Chimeras? I can do that with the precursor impurity measurement that PD has supported for a couple of years already. Well, if you assess the purity of a given MS2 spectrum solidly by the purity of its isolation window, then you might run into the problem that you are much more sensitive in MS2, and due to the limit in dynamic range that you have in MS1, you just didn't observe a co-isolated peptide, but it's still there, and it steals some of your intensity of the TMT reporter ions. So in MS2, you can detect that peptide because you focus your quad on a specific area in your MS1 range. You're much more sensitive, and hence can be much more sure that you've actually detected a interference. So yeah, Chimeras will offer you, to put it in simple terms, a better way to assess the purity of a scan with the help of deconvolution.
Thank you very much, Martin. And I guess, well, we don't have any more questions, but I would like to thank you all for joining our webinar. Thank you, Martin. I will also share my screen. I will have, I will share now in our chat a link where you can share your feedback with us. I hope this will give us some insights so we can continue delivering content that meets your expectations. Also, the webinar recording will be on our YouTube channel soon, and you will receive an email with the recording within a week or so. And thank you very much again. Stay tuned for more updates from MSA. Thank you all, and have a great day.
Thank you very much. Bye-bye.